Ceramics are one of engineering's greatest frustrations. They're strong. They're heat-resistant. They don't creep the way metals do. But they have a reputation for one unforgivable failure mode. When a crack starts, the part can fail catastrophically. Now here's the counterintuitive part. Researchers have shown that if you take a 3D printed ceramic lattice, an architected structure, not a solid brick, and add an ultra-thin polymer coating, you can make it dramatically more damage tolerant. Not by making the ceramics softer, not by turning it into a bulky composite, by changing how cracks initiate and how they spread. We're talking about a coating on the order of tens of micrometers, thin enough that, visually, the part still looks like a ceramic, yet mechanically, it can behave like a different class of material. It can absorb far more energy before it fails. That's the real breakthrough. Not ceramics become unbreakable, but brittle failure turns into controlled damage. And if you're an engineer, you already know why that matters. Damage tolerance is what separates a lab material from real-world material. So how can a thin, soft layer change the failure behavior of a brittle structure? And what does this unlock that ceramics couldn't do before, especially in heat, aerospace environments, and high-performance devices? Let's unpack the science carefully, because once you see the mechanism, the result stops feeling like a trick and starts feeling inevitable. This matters because ceramics sit right at the edge of multiple industries, yet brittleness keeps limiting where we trust them. In aerospace and high-temperature engineering, we want materials that are light, stiff, heat-resistant, and stable under extreme environments. Ceramics check many of those boxes until impact, vibration, thermal shock, or a tiny defect triggers a crack. In medicine, ceramics can be biocompatible and wear-resistant, but brittle failure is unacceptable in load-bearing or long-life applications. And in manufacturing, especially additive manufacturing, the problem gets worse. New design path. Use architected geometry to control how stress flows. Use a thin conformal polymer to manage crack initiation and propagation. And turn catastrophic failure into a slower, more predictable damage process. Printing can introduce small defects, and brittle materials don't forgive defects. They punish them. So the promise here isn't a new ceramic. It's that shift, catastrophic to graceful, is the difference between a demo and a deployable material. But this didn't come from random tinkering. It came from looking at how nature solves the brittle but tough problem. Nature builds with brittle minerals all the time. One of the classic examples is nacre, the inner layer of some shells. Nacre is made from brittle mineral plates, yet can resist cracking far better than you'd expect. The lesson isn't minerals become rubber. The lesson is architecture and interfaces, nature uses, layered structures, control weak interfaces, and energy-dissipating pathways. To force cracks to do more work, to twist, branch, slow down, and lose energy, rather than slicing straight through. Researchers in bio-inspired materials science have been chasing that strategy for years. Don't just ask, what is a material? Ask, how does failure move through it? In this case, the key insight was surprisingly simple. If brittle lattices fail because cracks run unchecked along surfaces and struts, then the fastest way to change behavior is to engineer the surface and the interface. Not with a thick coating that changes everything, with a thin conformal layer that changes the first moment of damage, when cracks usually gain momentum. That's the aha behind this work. Tiny interface engineering can control large-scale failure behavior. Now, let's break down the mechanism. Brittle failure starts at stress concentrators. In ceramics, the initiating defect can be microscopic. A tiny surface flaw, a pore, an edge imperfection. Anything that concentrates stress. A thin polymer coating can help in 3 practical ways. 1. It blunts stress concentrations of the surface. If the polymer fills or smooths micro defects, the peak stress at those sharp points can drop. That delays crack initiation. 2. It changes the crack path. When a crack reaches an interface between stiff ceramic and softer polymer, it may deflect, branch, or spread along the surface rather than cutting straight through the structure. That forces the crack to expend more energy. 3. It introduces controlled dissipation. A polymer can deform and absorb energy that a ceramic cannot. Not enough to turn the ceramic into rubber, but enough to convert instant fracture into progressive damage. The key is that this is happening on an architected lattice. In a lattice, failure doesn't need to mean total collapse. If damage is compartmentalized, the structure can maintain load pathways longer. So the coating isn't making ceramics flexible. It's changing the failure mode from brittle snap to controlled, energy-absorbing degradation. That's damage tolerance. And that's why this doesn't feel like normal coated ceramic thinking. The geometry is doing one job, the coating is doing another, and together they change the outcome. Here's the surprise. This isn't a bulky composite. It's not a thick laminate. It's a brittle structure with a thin, continuous surface layer. And the outcome is massively different. That tells you something important about materials engineering. A small change in the right location, where failure starts, can dominate the entire performance of a structure. If cracks are born at surfaces and interfaces, then surface engineering can rewrite the whole story. So the wow isn't polymers make ceramics strong. The wow is you can redesign failure without changing the base material. And if you can redesign failure, you can design ceramics for environments we usually avoid: impact, vibration, imperfect manufacturing, real life. But the video only earns that claim if we talk honestly about the engineering trade-offs and the bottlenecks that stand between a lab breakthrough and a flight-qualified part. There are two levers here and both matter. Lever 1, the printed ceramic architecture. A lattice can be designed so load spreads across many struts rather than concentrating in one brittle region. Architected materials can be tuned. Stiffness, strength, and energy absorption can be shaped by geometry. Lever 2, the interface behavior. A conformal coating changes local stress distribution, crack initiation, and crack growth. But it also depends on adhesion, uniform coverage, and compatibility under the environment the part will see. This is why the breakthrough is best understood as a system. Ceramic structure plus polymer interface plus manufacturing quality. That's also why the 70 micrometers detail is meaningful. It suggests a mechanism is not add thickness until it's tough, but add enough to control cracks and dissipation. But the most important engineering idea here is failure management. Instead of one crack causing instant catastrophe, damage becomes distributed and progressive. That's how aircraft structures and safety-critical systems are designed to survive. Not by never being damaged, but by failing the way you can predict. Behind a result like this is rarely a single genius moment. It's a team pushing through measurements that don't flatter brittle materials. Because brittle materials punish overclaiming. You don't get almost, you either survive the test or you don't. What made this kind of work impactful is that it reframes the brittleness problem in a way engineers can use. Where cracks start, how cracks move, how interfaces change the game. And it's deeply aligned with the modern materials trend. Stop thinking of material as only chemistry. Think of material as architecture plus interface plus process. That's why research like this tend to come from labs that blend additive manufacturing, mechanics, and bio-inspired design. Because the win isn't one ingredient, it's the system. Now, where does it realistically matter first? Let's keep the applications grounded. This doesn't mean every ceramic part becomes amazing. The best early applications are the ones where the combination makes sense. 1. Lightweight, high-temperature structural components, niche aerospace. If the ceramic carries load and faces heat, but historically fails too brittly under impact or handling, damage tolerance changes the adoption math. 2. Protective structures where progressive failure is safer than snap failure. In safety-critical designs, gradual damage is often preferable to sudden fracture. 3. Medical and biointerfaces, select cases. Not bone implants tomorrow, but specialized devices where ceramics are already used for where resistance or biocompatibility and where controlling brittle fracture could expand design options. 4. High-temperature industrial parts. Heat exchangers, thermal management structures, or environments where metals soften, if long-term coating stability checks out. Notice the repeated condition. This becomes real where the environment doesn't destroy the polymer. The coating can be applied consistently, and the lattice can be produced at scale with reliable quality. Which brings us to the honest tension point. 3 big questions decide whether this leaves a lab. 1. Scalability and throughput. Architected ceramic printing can be slow. If you can't make enough parts fast enough, it stays niche. 2. Long-term coating integrity. A polymer interface must survive the environment. Temperature cycling, humidity, UV exposure, chemical exposure, mechanical fatigue. If the coating cracks, delaminates, or degrades, the benefit may fade. 3. Certification and repeatability. Aerospace and medical adoption requires standards, qualification, predictable failure behavior, and quality control. That's slow by design, and it should be. Also, this approach won't fit every ceramic. Different ceramics and different polymers behave differently. Adhesion and thermal expansion mismatch can make or break the concept. So the promise is real but conditional. And the real breakthrough is not that it breaks physics. It's that it uses physics, stress interfaces, fracture mechanics in a smarter way. Here's the clean takeaway. They didn't invent a new ceramic. They engineered how ceramics fail by combining an architected 3D printed ceramic lattice, which spreads load and provides redundant paths, with a thin conformal polymer layer, which delays crack initiation and changes crack propagation. They shifted the failure mode from catastrophic brittle fracture to progressive damage with high energy absorption. That is a fundamental upgrade, because materials don't become useful when they're strongest. They become useful when engineers can trust how they fail. And this result is a blueprint for a larger trend, architected materials and interface engineering, where geometry and surfaces are treated as first-class design variables. In the next 5 years, expect this to remain mostly in prototypes and specialized demonstrations, especially where weight and performance justify high cost and low throughput. In 10 years, if manufacturing scales and coating durability is proven, you could see it move into select commercial niches, high-value components, specialized aerospace structures, harsh environment industrial parts. In 20 years, the bigger impact may be broader than ceramics. This method, architected structure plus engineered interface, can spread to other material systems, metals, polymers, composites. The principle is portable, even if the exact chemistry changes. So the future isn't one miracle part. It's a new design rule. Stop asking only what a material is. Start asking how it fails, and how you can control that. This story connects directly to the future Ford world. Additive manufacturing as performance design, not just shape making. Metamaterials where geometry produces properties. Self-healing and damage-tolerant systems. Bio-inspired strategies that engineer interfaces, not just bulk chemistry. The future of materials is increasingly system design, not single substance discovery. If you're an engineer or a student, this is the mindset shift. Progress isn't only a better material. It's better control of failure, variability, and interfaces. And if you're not technical, here's the simple version. A tiny coating didn't make ceramics stronger. It made ceramics survivable. That's what turns brittle breakthroughs into real products. Ceramics have always been a trade. Incredible performance with an unforgiving failure mode. This work doesn't erase that trade. It gives engineers a new option. Redesign the structure, redesign the interface, and force cracks to behave differently. That's the pattern Future Forge Explored tracks. How the future gets built, not by breaking physics, but by using it more intelligently than we used it before. Subscribe if you want the next layer of the story, because the same architected plus interface logic is now reshaping metals, polymers, and even electronics. The future isn't one material. It's a new way of designing matter.